Welcome to today's deep dive, everyone. So we are grounding today's discussion in this really fascinating piece of clinical source material.
Yeah, it's honestly an incredible look into the realities of a medical procedure.
Right, it really is. It's a procedural video transcript by Dr. Gautamukola S. Raju, and the specific title is HCC 1475-34C FB removal snare.
I know it's a very technical title.
Catchy, right. But the scenario it presents, it just immediately challenges, all of our assumptions about modern surgical environments.
Oh, totally. We have this idea of what a high-tech operating room looks like.
Exactly. Like if you, God forbid, swallow a rigid 6-inch plastic pen, you'd probably assume the instrument they use to pull it back up is, I don't know, some highly specialized robotic claw.
Right, like a laser-guided grappling hook or something.
Yeah, but it isn't. The primary tool for this extraction is often just a simple loop of wire manipulated by a human hand.
The endoscopic snare.
The snare. And the mission of our deep dive today is to unpack the mechanics, the physics, and really the unsung heroism of this single medical device.
It's just so adaptable. It really forces you to reevaluate what elegance actually looks like in a clinical setting.
I mean, I am just fascinated that a tool meant for one specific medical task can be adapted, on the fly, to solve these bizarre emergencies.
Right, because we tend to equate medical advancement with hyper-specialization. The idea that every single anatomical problem needs a uniquely engineered, single-use device.
Uh-huh.
But the reality of operating inside the human GI tract, it demands a level of real-time versatility. You just can't get that from heavily specialized tools.
So it's about efficiency.
Exactly. The snare shows how procedural efficiency is often about maximizing a basic mechanical principle rather than, just throwing more complex variables into the room.
Well, I want to look at how that efficiency plays out in a routine scenario first, before we get to the swallowed pens.
Sure.
Because the source material establishes the snare's everyday primary function, which is during a polypectomy.
Right, removing a polyp.
Yeah. So when an endoscopist removes a large pedunculated polyp one with a stalk, right?
Right, exactly, like a mushroom shape.
Okay, got it. So the snare is the cutting tool. You lasso the tissue, you cut it, and instinctually you'd think the next step is to pull the cutter out and put in a dedicated retrieval device.
Like a specialized net.
Yeah, to catch the piece you just cut off.
That's the traditional way of thinking for sure. You use a blade to cut, a basket to catch.
Right.
But introducing a second tool creates all these procedural inefficiencies. I mean, pulling the snare out, feeding a net down the scope, deploying it, it all takes time.
And the patient is under sedation that whole time.
Exactly. Every extra minute carries compounding risks for the patient. So what the technique here shows is this seamless pivot.
Okay, so what do they do?
Because that pedunculated polyp leaves a remnant stalk after it's cut, the endoscopist doesn't even need a net. They use the exact same snare, relasso the remaining stalk, secure their grip, and pull the whole thing out.
Okay, let's unpack this for a second, because it's like using your spatula to both flip the pancake and then carry all the way to the breakfast table.
That's a great way to put it.
Like instead of dirtying another dish. But doing so in this case actually saves the patient money, right?
Oh, absolutely. It eliminates the need to open a secondary sterile piece of equipment. Every time you break the seal on a single-use retrieval net, that gets added to the patient's bill.
Wow. And I imagine it helps the environment too.
Massively. The volume of biohazardous waste from disposable endoscopic accessories is staggering. So adapting the existing tool reduces costs, cuts medical waste, and shortens the anesthesia time.
That's incredible. But wait, I have to challenge the mechanics of that spatula analogy for a second.
Okay, go for it.
If you are using a braided wire loop that was literally just used to slice through human tissue, aren't you running a massive risk of just accidentally amputating the stalk entirely when you try to grip it?
You mean cutting it again by mistake?
Yeah. How do you use a cutter as a clamp without cutting?
Well, that's where the tactile proficiency of the operator is just critical. It comes down to modulating the applied tension. When you cut, you use electrocautery and decisive force. But during retrieval, the assistant manipulating the snare handle has to apply just enough tension to grip the stalk without shearing it.
So they have to have an amazing feel for the tool.
Right, a highly calibrated physical intuition. But unlocking that efficiency requires flawless synchronization. It's not just a solitary physician operating a joystick.
Right, because it's a bifurcated process. Let's dive into that division of labor. This is where the biomechanics of the tool intersect with the humans in the room.
Yes, the human element is huge here.
Because the mechanism is simple, right? Opening and closing a hand. a wire loop inside a catheter. The assistant pushes a handle to open it, pulls to close it.
Correct.
But the source emphasizes that the pacing, specifically opening and closing slowly, is the single most critical safety factor. Why is slow so important?
Think about the spatial constraints. The endoscopist is looking at a live video feed on a monitor, navigating the 3D geometry of the GI tract. But the assistant is standing beside the bed, managing the physical handle, completely blind to the inside of the body.
Oh, wow. They can't see what they're doing.
Usually they are just watching the endoscopist or the main monitor, but they don't have that direct immersion. If the assistant rapidly deploys the snare, the wire loop vigorously expands.
And if it's pressed against a wall.
Exactly. If the tip is deflected against the mucosal wall of the colon, that sudden expansion of stiff wire can easily cause a tear or even a perforation.
So what does this all mean? The person holding the tool and the person looking at the screen have to be in a complete mind meld.
Total synchronization.
If I'm driving and my passenger suddenly yanks the steering wheel, we crash. It's a literal tango inside the GI tract, right?
That's exactly it. It's an endoscopic tango. The slow opening gives the endoscopist time to react. They see the wire deploying on the monitor, assess its trajectory, and make micro adjustments to center it.
So if the assistant pops it open too fast, they rob the doctor of that reaction time.
Precisely. It creates a need for this nonverbal communication, a shared internal metronome. They have to pace their movements perfectly to navigate the unpredictable variables of the human body safely.
Okay, that shared metronome makes total sense when we're talking about retrieving a soft, pliable polyp. But here's where it gets really interesting, because the source material escalates this.
It really does.
The snare isn't just for soft tissue. It's used to remove plastic biliary and pancreatic stents, and even to extract long foreign objects.
Right, like the swallowed pens and pencils you mentioned earlier.
Exactly. And trying to grab a pen with a wire loop, we go from a carefully placed medical stent to someone swallowing a pen.
It completely inverts the biomechanical problem.
Right. A pen is smooth, slick, and rigid. A wire loop seems like the worst tool for that. How does it not just slip off?
Well, with a medical stent, you can snare the pre-molded flaps on it. But with a pen, the operator has to visually hunt for a purchase point.
Like the pocket clip?
Yeah, the pocket clip or the ridge near the ball point. And then the assistant has to lock the snare down with intense, sustained tension.
Just to get enough friction.
Exactly.
Yeah.
But honestly, gripping the object is the easiest part.
Right, because once you have a 6-inch rigid cylinder, you have to drag it out of the body. And the crucial technique here is perfect alignment.
The scope, the snare, and the long object must be perfectly aligned with the longitudinal axis of the gut.
It sounds exactly like trying to carry a long, rigid ladder around a tight corner in a winding, narrow hallway.
That is the perfect analogy. The physics shift entirely when dealing with rigid long objects compared to soft tissue. A soft polyp deforms. A pen acts as a rigid lever.
So if you pull it while it's angled across the lumen,
The ends of the pen will immediately dig into the delicate mucosal walls. It doesn't extract the object, it drives the blunt ends deeper, risking a catastrophic perforation.
basically punching through the drywall of the hallway.
Yes, and the GI tract is nothing but turns and acute angles.
Which brings us to manipulating the obstacle course, because these tight corners make alignment incredibly difficult.
Very difficult.
The source identifies the high difficulty areas for long objects as the GE junction, the gastroesophageal junction, the cricopharynx, and the pharyngo-oral pathway.
Right, and as you navigate those areas, you can't just rely on the internal manipulation of the scope anymore.
Wait, really? What do they do?
The medical team actually has to alter the external geometry of the patient's body.
Okay, wait, so it's not just the endoscopist doing the work inside. The anesthetist actually has to physically manipulate the outside of the body.
Yes, they have to physically step in.
Like tilting the neck and jaw to straighten the hallway so the ladder can get out.
Exactly. Retrieving a foreign body is a full team, full body spatial puzzle.
That is wild.
Let's take the cricopharynx and pharynx. The pharynx naturally curves forward toward the mouth at roughly a 90-degree angle to the vertical esophagus. If you try to drag a rigid pen straight up the esophagus and around that 90-degree bend, the distal end of the pen will act like a spear against the back wall of the throat.
Oh, God. So they're completely bottlenecked. They can't magically make the pen bend.
Right, so the anesthetist or an assistant at the head of the bed intervenes. They extend the patient's neck and apply a firm jaw thrust.
I've heard of a jaw thrust in CPR training, but here it's serving this highly specialized biomechanical purpose.
Yes, they are taking hold of the mandible and forcefully pulling the entire lower jaw forward.
Wow.
Because of how the muscles and ligaments are tethered, pulling the jaw forward pulls the base of the tongue and the larynx with it. Combined with extending the neck, they are mechanically forcing that natural 90-degree curve into a straight vertical cylinder.
They're temporarily remodeling the patient's anatomy. That is just profound.
It really is. It stops being just a minimally invasive internal surgery.
Right. The endoscopist is gripping the pen internally, relying completely on the anesthetist to forcefully stretch and align the throat externally.
Exactly. Creating a fleeting, straight corridor just wide enough for the rigid object to clear the airway.
That is incredible teamwork. Okay, so the neck is extended, the jaw is thrust forward, the pen comes out. You think, okay, high fives all around, procedure's over.
You would think so, but no. The protocol mandates that the procedure is not over.
Right. The crucial final sweep.
Whenever a long, rigid object is removed, it is a mandatory practice to go back in with the scope.
It's the ultimate leave no trace check. You've successfully removed the intruder, but you have to walk back through the house to make sure the walls didn't get scratched on the way out.
That's exactly why they do it. Medical success isn't just about removing the problem. It's about confirming you haven't created a new one.
Right, so they re-examine the specific anatomical bottlenecks, the GE junction and the cricopharyngeal area.
Because those are the high-friction zones. The shear force exerted by the hard plastic against the delicate esophageal mucosa is immense.
Even with the perfect jaw thrust.
Even with the jaw thrust. So the endoscopist goes back down to hunt for microabrasions, tearing, or an outright perforation.
Because if you miss a perforation there...
The clinical consequences are catastrophic. The esophagus doesn't have the tough outer lining that the rest of the bowel has. Any breach allows bacteria to leak directly into the chest cavity.
Right, near the heart. That's a massive mortality risk.
Absolutely. So true procedural success is defined by the extraction coupled with the visual verification of structural integrity.
So wrapping up this journey for you, the listener, we took a deep dive into a single medical video about a simple snare, and it revealed this fascinating world.
A world of incredible medical efficiency and precise teamwork.
From polyps to pencils, it really shows the adaptability of these tools and the professionals using them.
They're constantly reading tissue resistance, adjusting to rigid geometry, and just dynamically solving problems.
And that leaves us with a final provocative thought to mull over. We're currently seeing this massive push toward fully automated robotic surgeries and AI-driven procedures, right?
Oh yeah, it's everywhere in the literature now.
But the source material implies such a high level of unspoken physical coordination in the operating room. We talked about that shared metronome, the tactile feedback loop between the endoscopist, the assistant on the handle, and the anesthetist holding the jaw.
Right. They are relying on the physical tension of a wire and the subtle resistance of a mucosal wall. It requires a synthesis of thousands of sensory inputs.
Exactly. So how much of modern medicine relies not just on advanced technology, but on that silent, physical choreography?
Can an AI ever truly replicate the tactile intuition needed to ease a rigid object around a delicate curve?
Or will the messy, unpredictable reality of human anatomy always require that elegant physical tango of a human surgical team? It's definitely something to think about. Thanks for joining us on this deep dive, and we'll see you next time.